This lecture focuses on Chapter 5 of Foundations of Measurement. The title of that chapter is Probability Representations. There is a great deal more material in the chapter than can be covered in a single lecture. I'll concentrate on the foundational elements and the most general considerations. Many of the details will not be covered, and one needs to go to the chapter to uncover those. This chapter deals with a fundamental problem in the theory of measurement, a problem, as we shall see, that is closely related to the foundations of probability. I'll come to that in a moment. I want to begin with some preliminaries. These preliminaries in probability theory, elementary probability theory, will be familiar to many of you, but in order to have a frame of reference we can refer to and to review the concepts for those who have not seen them recently, we'll begin with these elementary preliminaries. To start with, we say that if we have a non-empty set X and a non-empty family of subsets of X, script E, we then say that E is an algebra of sets on X if and only if for any two sets A and B in the family E, the closure of A, the complement of A, is in E, and the union of A and B is in E. Now notice what those two conditions just say. That in order for a family of sets, subsets of X really, to be an algebra of sets, two closure conditions have to be satisfied. One closure condition is that if a set is in the family, its complement is in the family, and the second is that the union of any two sets must be in the family. It's very easy to show that other things we then expect follow about the closure of E. For example, X itself must be in E. Remember, E is non-empty, so if we take any set A in E, its complements in E, we take A union the complement of A, that's X itself, then that must be in E, and so forth. And the complement of X is the empty set, so the empty set has to be in E. So we know always that both X, that is the whole set or the whole space as we'll say, and the empty set have to be in E. The elements of E we'll call events, and we'll want to talk about the probability of events. Technically, we say that E is a sigma algebra of sets. Sometimes we'll say a sigma algebra of events if E is closed not only under finite unions but under countable unions, so that if there's a countable sequence of sets, the union of that countable collection is itself in E. It's important to note here that there are other ways of talking about the fundamental objects to which we attach probability. There is a long history of talking about propositions, for example. But since the work of Kolmogorov on the foundations of probability in the early 1930s, it's been especially the case that the formal theory of probability is formulated in terms of events, where events are regarded as sets of possible outcomes. Another way of talking about the set X is X represents the set of possible outcomes, and then elements of E represent events. They're subsets representing sets of possible outcomes, and that's the characteristic of an event. For example, if we flip a coin 2 times, then we would have, we can put it right up here I think, we would have 4 possible outcomes. Heads, 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 tails, tails, heads, tails, tails. And that set of 4 elements would be X. Now the event of getting a head on the first flip would have been the possible outcomes HH and HT. And of course A is a subset of X. Most of you will be familiar with that concept of event. We introduce probability by definition 2, a triple XEP, where X is a non-empty set, E is an algebra of sets on X, and P satisfies the conditions to be stated in a moment. Such a triple is a finitely additive probability space if and only if, for every two events A and B and E, familiar conditions hold. The probability of A, and this is of course the numerical probability, notice the condition is that P is a real valued function from E to the real numbers, and in particular it'll be on the interval 0 to 1 because P, for any event A, it's non-negative, the probability is equal to or greater than 1, and the probability of the whole space X is equal to 1. The third axiom is the familiar additivity property for disjoint events. If the intersection of A and B is empty, then the probability of A union B is simply the probability of A plus the probability of B. As we'll see in some of our later discussion, this condition that the intersection must be empty, and we don't have unrestricted additivity, is a troublesome feature of probability theory. As in the case of the algebra of events being a sigma algebra, if it is closed under countable unions, we have a familiar and standard condition on the probability space. The space we defined by the three axioms is finitely additive. It's said to be countably additive if, in addition, the following two further axioms are satisfied. Axiom 4, E is a sigma algebra on X. Axiom 5, if we have a sequence of events in E such that they're pairwise disjoint, that is, A sub I intersected A sub j is empty for I n equal to j, then the probability of the union of the sequence is equal to the sum of the elements, where in general here the sequence is infinite. And we won't say too much about countably additivity, but it's important to have this condition in front of us for work in many scientific contexts with probability theory. It's essential to have not only finite additivity, but in the standard framework, countable additivity. Now, these are preliminaries that'll be familiar to most of you, and are concepts that we'll want to refer to again and again. The measurement problem, or the measurement approach to probability, now consists of the following. We have a qualitative relation, which we'll write in the usual way, and read A is at least as probable as B. Now, there can be various interpretations of this qualitative relation that we're going to study. One is it could simply be we make judgments of A being at least as probable as B when the relative frequency of A is at least as great as B numerically. Another example might be using a classical definition of probability the way in which Laplace and others did at the beginning of the 19th century and earlier. We have some principles of symmetry. For example, we appeal to principles of symmetry if we look at a symmetric die with the ordinary 6 faces. We say, well, the event of an even receiving an even number up on a throw of the die is at least as probable as the event of getting the face with 3 on it, 3 dots, say. And the reason we accept that judgment is because of some principles of symmetry that we accept about that die. A third and most general framework for making qualitative judgments is to regard these judgments as subjective or personal or as considered opinion. There are many such examples. When we ask a meteorologist to predict tomorrow's weather, the meteorologist will use a great deal of scientific information, a great deal of data gathered, in fact, from all over the world about the weather. But when he finally comes down to making a forecast for you, that forecast will be regarded as a judgment. And in many cases, forecasters are now giving probabilities in conjunction with their judgment, so that it is not unusual to see a forecast of the weather to say that the probability of rain tomorrow is at least 0.6. Now, those judgments can be regarded as based upon a subjective judgment or a personal judgment on the part of the expert, the meteorologist, assessing all of the information in front of him. There are many other contexts in which such personal judgments are made. A person investing in the stock market may decide to invest in one stock rather than another because of his judgment of the relative risk or the relative probability of an increase in value. When we decide to make all sorts of choices, such summations of many aspects of our experience enter into making what we can call and will call a subjective judgment. Now, in the second lecture, we'll put this discussion in more of a decision framework. In the present lecture, we will restrict ourselves just to the case of beliefs insofar as we're using the third interpretation. We'll restrict ourselves just to the case of qualitative probability judgments. We'll go on to the case of decisions, of talking about one act or one decision preferred to another in the second lecture. My point that's fundamental is that though in the current literature of the foundations of probability, the tendency is certainly to regard the qualitative interpretation, the qualitative relation, as primarily to be interpreted as a subjective judgment. That is not necessarily an interpretation that is forced upon us. The other two examples I've given, in terms of relative frequency or in terms of principles of symmetry, can also be defended and be used in such a qualitative context. Now, however we finally make that interpretation of the qualitative judgment, the fundamental representation problem is straightforward and is independent of the particular interpretation we give of the qualitative relation. What we desire is a set of conditions on the qualitative relation such that there is a probability measure, P, let's say, that strictly agrees with the qualitative relation. In the ordinary measurement sense, event A is judged qualitative at least as probable as B, if and only if the numerical probability P of A is equal to or greater numerically than P of B. Secondly, in terms of uniqueness, we want, in the best sense here, a very strong sense of uniqueness, that there is exactly one such measure. Because we think of probability as being uniquely defined with the probability of the whole space x being equal to 1. Notice that without P of x equal to 1, we might think of probability in terms of a ratio scale, but then, for example, the familiar relative frequency interpretation won't work if we have simply an arbitrary ratio scale. We'll have something more to say about that in the second lecture. The first problem we want to look at is the obvious qualitative features we would expect this relation to have. And the axioms that we'll look at are essentially due to Di Finetti, Bruno Di Finetti, the Italian statistician and probabilist who has done much fundamental work in this area over the last half century, really. Before we characterize such qualitative structures, there is one preliminary definition that is a generalization of what is discussed in the earlier lectures on extensive measurement that give us a way of formulating, for the present and immediate purposes, the Archimedean property. We say that a sequence of events, A1, ... A sub I, etc., is a standard sequence relative to the given event A, if and only if for every I equal 1, 2, etc., there exist events B sub I, C sub I in the family, or in the algebra of sets, such that these conditions are satisfied. A1 is equal to B1, and B1 is equivalent to A1. The intersection of BI and CI is empty. BI is equivalent to AI. CI is equivalent to AI. And AI plus 1 is equal to BI union CI. Intuitively now, with that in front of us, we want to get a closer and more intuitive interpretation of exactly what this means. If you remember our earlier discussion, AI plus 1 corresponds to I plus 1 disjoint copies of A. So as we go along, I plus 1 builds up and represents the union of these disjoint copies of A. Intuitively, we could write it this way. AI plus 1 is equivalent to I plus 1 copies of A. Now, in the case of math, we often write it that way. Here, we haven't given a direct interpretation of this, but this is the way we would think of it. I plus 1 times A, meaning I plus 1 copies of A, where those copies are disjoint. Now, there is one misprint over here in the definition we want to be careful about. C sub I in condition 4 should be equivalent to A and not to A sub I. The point of B sub I and C sub I is that A accumulates these disjoint copies, and C sub I adds another disjoint copy. So that's the way the mechanism works. B sub I corresponds to A sub I here, and then C sub I adds the new disjoint copy to give us AI plus 1. That's straightforward, and I don't want to spend too much time on it. There's a detailed discussion of this in Chapter 5, and that discussion follows the earlier discussions of standard sequences. Now, with that preliminary concept of standard sequence out of the way, we're in a position to define what we mean by a structure of qualitative probability, following this early work of DeFinetti. And we say that a triple X, E, at least as probable and as relation, where as usual X is a non-empty set, our probability space, and E is a algebra of sets or an algebra of events. We say that such a triple is a structure of qualitative probability if and only if for any events A, B, C, and D in E, the following three axioms are satisfied. First, the familiar axiom of weak ordering, that the relation at least as probable as is a weak ordering of E. We would expect that so that we can expect transitivity and the judgments of comparison always implied by connectedness. The second axiom, to avoid triviality, that X is strictly more probable than the empty set. Another way of saying this is that X, the certain event, because X must always occur, is strictly more probable than the impossible event, the empty set. And also that any event is at least as probable as the impossible event, the empty set, or the empty event. The third axiom is the qualitative analog of the quantitative axiom of finite addition. If A intersection B and A is equal to A intersection C is equal to the empty set, that is, if A intersection B is empty and A intersection C is empty, then B is at least as probable as C if and only if A union B is at least as probable as A union C. So notice how the additivity is expressed. We have the qualitative judgment about B and C. Then we can add to both sides, so to speak, to both B and C, a disjoint event A, and that inequality should be preserved. The intuitive appeal of that is obvious. If B has been judged at least as probable as C, then the addition of some event necessarily disjoint from B and C shouldn't change the direction of that judgment. Now we want to add an additional condition that such qualitative structures are Archimedean, and that we then want to examine what we can say about the representation of such qualitative probability structures. The final axiom for qualitative structures of probability is the Archimedean axiom, which uses the concept of standard sequence just defined. In particular, a qualitative structure is Archimedean if and only if, for every event with positive qualitative probability, that is, for every event A strictly greater in probability than the impossible event, any standard sequence relative to A is finite. So it's the finiteness condition on any standard sequence that gives us a way of expressing the Archimedean condition. An important fact about these four axioms for qualitative structures, including the Archimedean axiom, is that they are all necessary. That is, that if we assume the existence of a probability measure, it is easy to prove that the axioms follow as a consequence. That's left as an exercise. It's an important feature of the four axioms we stated. The axioms are necessary. A tougher and in many ways more important and interesting question is, are they sufficient? Or put another way, does every finite structure of qualitative probability have a representation in terms of a probability measure? Notice that with the restriction to finiteness, the Archimedean axiom is automatically satisfied, and we're therefore concerned with the first three axioms. The first three axioms being the axioms that De Finetti stressed as being of importance qualitatively. It was some effort to show that the answer is no. The question was open for several years, and in 1959, Kraft, Pratt, and Seidenberg gave a counterexample. A counterexample in the following sense. They gave an example of a finite qualitative structure satisfying the three axioms, that is, a weak order, the condition on the impossible event, and the certain event being strictly greater than the impossible event, any event being at least as probable as the impossible event, and the qualitative additivity condition. Those three axioms. They gave an example satisfying those three axioms, but such that no numerical representation could exist. Because it's not obvious how these axioms fail, that is, how one would construct an example that satisfied the axioms but did not have a numerical representation in terms of a probability measure, I think it'll be useful to go through this example. The example consists of a space with 5 atoms. It's easy to show that this is the smallest space. You can't do it with 4 atoms. So X consists of the elements A, B, C, D, and E. We can think of these as intuitively as our 5 possible outcomes. The events, the algebra of sets E, consists simply of all subsets of X. It is all 32. Now, we consider the ordering relation such that first, the 3 inequalities shown here in 1 hold. That the event A, I'll just say A is at least as probable as B and C together. C and D, not at least as probable, I'm sorry, A is strictly more probable than B, the event BC. The event CD is strictly more probable than AB, and BE strictly more probable than AC. Now, if there does exist a probability measure P, we would have immediately additivity, as shown here. The probability of A from the first inequality should be strictly greater than the probability of P plus the probability of C. From the second inequality, the probability of C plus the probability of D should be greater than the probability of A plus probability of B. And finally, the third one, the probability of B plus the probability of E, greater than the probability of A plus the probability of C. Now, adding these inequalities, these numerical inequalities, and canceling what's common to both sides, we obtain at once the new inequality. The probability of D plus the probability of E is greater than the probability of A plus probability of B plus probability of C. Now, this inequality is important. Notice that it uses all 5 atoms. On the assumption that we have a measure, we can then infer that in the order we must have then this qualitative inequality, namely the event consisting of D and E is strictly more probable than the event consisting of A, B, and C. Now, the trick is to find an ordering satisfying the first 3 inequalities, shown as 1, and violating 2, this consequence. But violating it in such a way that there is no event between DE and the event ABC. So that we can change in the order just this single pair. And so we can now have in the new order the event ABC strictly more probable than DE. And nothing else has changed and nothing else is affected. Well, in that case, because this is a consequence, 2 is a consequence, we've shown that no numerical representation could exist for that order, and yet all the axioms are satisfied. Now, the clever thing, and the Kraft, Pratt, and Seidenberg example, is to give a very clear construction of how this can be done. And let's look at their construction. We'll make a assignment. We won't bother to normalize x because it's easy to work with the integers. It's obvious how to normalize by dividing through. So we choose an epsilon such that epsilon is strictly between 0 and 1/3, and we let the numerical value of the whole space be 16 minus 3 epsilon. And then we make these assignments to the 4 atoms. P of A is 4 minus epsilon. P of B is 1 minus epsilon. P of C is 3 minus epsilon. P of D is strictly 2, and P of E is 6. It's important to note, if you think back to our example, A, B, and C were subtracting off epsilon. For C and D, we're not. Now, it's easy to check that under this numerical assignment P, our inequality 1 holds. Thus, for example, A is 4 minus epsilon, which is strictly greater than P of B plus P of C, which is 4 minus 2 epsilon, and so forth. You can easily check that. Secondly, we can check immediately that P of D plus P of E is 8. On the other hand, P of A plus P of B plus P of C is 8 minus 3 epsilon. That satisfies 2. Now, in order to satisfy the axioms in such a way that we can reverse that ordering, we can make the event ABC qualitatively strictly more probable than the event DE, we have to make sure that there's no distinct event, P of A, that lies between these two. Well, it's clear from knowing that P of the numerical value of DE is 8 and the numerical value of P of ABC is 8 minus 3 epsilon that we have to have an event PA equal to 8 minus I epsilon. But we notice that 8, in terms of the integer values of the atoms, can only occur in 2 combinations of 1, 2, 3, 4, and 6. Notice only those integers occur here. 1, 2, 3, 4, and 6 for the 5 atoms. And then for the case of 3 of them, we subtract epsilon. But 8 can occur, which must be here, in only 2 distinct ways. Must be, of course, distinct atoms. We can have 1 plus 3 plus 4 or 2 plus 6. But 1 plus 3 plus 4 is just ABC. 2 plus 6 is just DE. And therefore we conclude there can be no distinct A between these two, and we can reverse that ordering, violate the numerical representation, and thereby show, with this counterexample, it is not possible to prove that the axioms for a qualitative structure, the 3 axioms we've considered, with the Archimedean axiom being redundant in the finite case, that these three axioms are strong enough to give us a basis for proving a numerical representation theorem. Given the failure of the qualitative axioms of Di Finetti, together with the Archimedean condition, to be sufficient to guarantee the existence of a representing probability measure, it's natural to ask for sufficient conditions. And there's quite a history of the study of such conditions. In 1937, Di Finetti introduced the following axiom, which we'll call phi prime, and it was also introduced by the American mathematician B.O. Koopman, probably independently in 1940 in two papers. These papers are all referred to in Foundations of Measurement. And this axiom simply says that for every n, there is a partition, C sub 1 to C sub n, of the probability space X, such that the elements of the partition are equivalent, so that the partition divides the space into ever finer subsets. And notice the axiom holds for every n. So I pick any n, 15, 100, 10 to the 20th. There exists such a partition of equivalent elements, equivalent in qualitative probability. That, of course, is a very strong axiom. It's also evident that such an axiom is not necessary. It's easy to give examples in which it isn't necessary. It's not even necessary, of course, in the case when the set X is infinite. Clearly, it's an implication of this axiom phi prime that the structure of qualitative probability be infinite. In a certain mathematical way, it's a natural condition. But it also, we have to recognize, is a very strong kind of regularity condition that is in no sense necessary. Now, Savage, it's Leonard J. Savage, in 1954, in his well-known and influential book, Foundations of Statistics, introduced a related but different axiom, which we'll call phi double prime. And that is under, again, the assumption that we have a structure of qualitative probability. If A, B, and B are events, and A is strictly more probable than B qualitatively, then there exists a partition of C1 to Cn of the space X such that we can add the elements of the partition to B and not change the inequality. That is, the partition is sufficiently fine that no matter how close B is to A in qualitative probability, the events can be added, as shown here, to B. If we take any of those events and add them to B, we still will not be as probable as A. That's obviously a related property. Savage pointed out that you could think of this axiom being satisfied by rolling a fair die n times for the n required here. And of course the axiom phi prime would require directly that for any n we could roll the die n times and get such a partition. That'd be one way of realizing axiom phi prime. Now, though, it's interesting that though axiom phi prime, Savage's axiom, only calls for the existence of a partition with n elements, whereas axiom of Di Finetti and Koopman requires a partition for each n. In fact, you can show that Savage's axiom implies axiom phi prime. And the important fact about both these axioms, whether we're talking about the Di Finetti-Koopman axiom or the Savage axiom, is that necessarily they imply that the structure of qualitative probability is infinite. That is, that the set X is infinite. Now, in 1967, Duncan Luce introduced a weaker axiom that is also sufficient. This axiom is a little more complicated to formulate, as one might expect from its being weaker. So again, if we have a qualitative structure of probability, I haven't written that down, but that's assumed here, and if A, B, C, and D are events and are such that A and B are disjoint, and A is strictly more probable than C, and B is at least as probable as D, then there exist events C prime, D prime, and E prime such that these four conditions are satisfied. E is equivalent in qualitative probability to the union of A and B. C prime and D prime are disjoint events. C prime union D prime are contained in the event E. C prime is equivalent to C, and D prime is equivalent to D. This axiom can be satisfied in finite structures, though not really in most finite structures, but it's easy to show there exist finite structures in which the axiom is satisfied. Luce also showed originally in his 1967 paper that axiom 5 is strictly weaker than Savage's axiom just stated. Now, Luce proved at the same time Theorem 1, this is Theorem 1 of Chapter 5 of Foundations of Measurement, that if we have a Archimedean qualitative probability structure satisfying his axiom 5, then there exists a unique representing measure P. And the proof of that is given in Chapter 5. Now, even though Luce's axiom 5 is weaker than either the Di-Finetti-Koopman axiom or the Savage axiom, as stressed, it is sufficient but not necessary. It's natural to look for a simpler axiom, and also very desirable to have axioms that are both necessary and sufficient for either the finite or infinite case. In fact, we would like, in general, a unified treatment. Well, since the appearance of Foundations of Measurement in Volume 1 in 1971, Mario Zanotti and I published an approach that gives simple, necessary, and sufficient conditions by an extension of the algebra of events that I want to consider, and importantly uses very directly the basic theorem on extensive measurement that was stated by Duncan Luce in the first lecture on extensive measurement. Let's discuss what this approach is, because the conditions are very simple and use in a direct way the theory of extensive measurement. The first step is a very simple one. Instead of considering events, we consider the indicator functions of events. Now, what are the indicator functions? The indicator function of event is just a real-valued function defined on x, such that for each element of x, the value of the function a super I, we'll use I for indicator, a super I is 1 if x is in A, and 0 if x is not in A. That's a familiar concept. Sometimes, by the way, in the older literature, such indicator functions are called characteristic functions. And in fact, in the literature on set theory, they're usually called characteristic functions. In a probability context, we call them more adequately indicator functions, because there's a different and important concept of characteristic function in probability theory. Now, if we just use the indicator functions as such, the algebraic structure is just the structure of the events, because there's a direct one-to-one correspondence between the events and the indicator functions. The important extension is to close the indicator functions under functional addition. So if we have two indicator functions, a super I and b super I, we consider their sum. And their sum, of course, is in general no longer an indicator function, because the value of this sum in general could be 2 as well as 0 or 1. Formally, if we're given a space X or a set X and E as the standard algebra of events or sets on X, we let E starred be the smallest set of functions such that defined on X, such that if A is in E, that is if A is an event, then the indicator function of A is in E starred. And secondly, that E starred is closed under addition. That is, if A starred and B starred are two functions in E starred, then the functional sum, A starred plus B starred, is also in E starred. That's just saying formally what I said above about closing the indicator functions. From a probability standpoint, we call such functions in E starred extended indicator functions. But these extended indicator functions are just a very restricted set of random variables. What kind of random variables are they? They are just random variables that have non-negative integer values. And we want to qualitatively order. Now, not the probability, of course, the random variable. That's not the correct way of talking about the random variables, but their expectations. So the extension here is from events to a very restricted set of random variables, and from probability to expectation of these random variables. So we can talk about the expectation of A starred and the expectation of B starred, or if we had two such functions, A starred plus B starred, then of course we expect the expectation function to have the expected additivity property. Now, what we want in terms of a representation is that qualitatively, the qualitative expectation of A starred is judged to be at least as great as the qualitative expectation of B starred if and only if the expectation of A starred is at least as great as the expectation of B starred. The properties we want this expectation function to have, we now want to review before looking at the axioms on this qualitative relation of expectation. The three properties of an expectation function that we need are that the expectation of the impossible event is of the indicator function of the impossible event is 0. The expectation of the indicator function of the certain event is 1, and the additivity property that the expectation of two extended indicator functions, A starred plus B starred, is equal to the expectation of A starred plus the expectation of B starred. Notice, of course, that the expectation function in general should be a linear function. It needs more than this additivity property. But for our restricted purposes here, only this additivity property is required. Given such an expectation function for these very restricted random variables, these non-negative integer valued random variables we're considering, we then can define immediately the probability of an event as simply the expectation of its indicator function. Notice, of course, that when we talk about the expectation of an indicator function, strictly of an event, that expectation must lie between 0 and 1. For our extended indicator functions in general, there is no bound on the possible upper value of such indicator functions. In fact, it's easy to see that the situation is unbounded for our extended indicator functions by just taking n sums of the indicator function of x. It's natural to ask, what has happened now to the concept of probability? In the ordinary textbook treatments current today, expectation of random variables is always defined in terms of the measure on the sample space, or on the probability space, the measure p. Here, we're doing exactly the opposite. The primitive or fundamental concept is expectation, and we're defining probability in terms of expectation. It's important to emphasize two things about this. First, that historically, such a definition of probability in terms of expectation is not new. It goes back to Huygens in the 17th century and to the Reverend Thomas Bayes in the 18th century, just to mention two prominent individuals. In fact, both Huygens and Bayes thought that the concept of expectation was the sound and clear concept, and we should therefore use expectation to define the less clear and less well understood concept of probability. The second point is that in ordinary talk about quantitative properties, expectation and not probability is the usual concept, the concept we use in ordinary talk. Let me give two examples. If I want to talk about how much weight I shall gain or lose on a summer vacation, I don't give the probability distribution of that quantitative function. The most I will say ordinarily would be expectation. I expect to gain 5 pounds, or even better, I expect to lose 2 pounds. Secondly, in talking about a child, for example, how tall do you expect this child to be as an adult? We don't give a probability distribution on height, even though, of course, from extensive developmental data, we could generate such a distribution. For ordinary talk, we're contented to speak only of the expectation. I expect my daughter to be about 5 feet 6 inches, etc. We don't talk in terms of anything like the full distribution. The point is that when we're dealing with quantitative concepts and also probabilistic concepts at the same time, it is expectation that melds these two together, the concept of expectation, and it is natural to make this well understood and very much used ordinary concept of expectation fundamental rather than probability itself. It's important to also recognize that in physics, as a third general point, in physics the concept of expectation is really the one that is fundamental rather than the concept of probability. Now, let's proceed then, corresponding to our development of a structure of qualitative probability, to develop a structure of qualitative expectation. And the parallelness will be very apparent. Let X be a non-empty set as before. Let E be an algebra of sets or events on X. And let us have the usual binary relation, but now not on E, but on E starred. We'll call this the qualitative expectation relation. Then we say that a triple, X, E starred, the binary relation of qualitative expectation, this triple, is a qualitative expectation structure corresponding to a qualitative probability structure if and only if for every A starred, B starred, C starred in E starred, the following 4 axioms are satisfied. And now as we look at these axioms, we'll see they're an exact parallel for the 4 axioms discussed earlier for qualitative probability structures. But as we shall see in this case, they are not only necessary, but sufficient to have a numerical representation. Axiom 1 is that we have the usual weak ordering. Axiom 2 is just that the indicator function of the certain event is strictly greater in expectation, qualitative expectation, than the indicator function of the impossible event, and that for any event A, the indicator function of that event is at least as qualitative, at least as great an expectation as the expectation of the indicator function of the impossible event. Notice axiom 2 is just a completely direct translation of axiom 2 for qualitative probability structures. Now the critical change and the really important change is in axiom 3. Axiom 3 says unrestrictedly that if extended indicator function B starred is at least as great an expectation qualitatively as C starred, if that's if and only if A starred plus B starred is at least as great an expectation as A starred plus C starred. The important point is that we now add A starred to both sides in this functional addition in an unrestricted manner. And this is really the critical change in many ways, that we don't have a restriction to A and B being disjoint events and A and C being disjoint events. We have an unrestricted axiom, as we have in the case of the abstract case of extensive measurement. And finally, axiom 4 is just an appropriate form of the Archimedean axiom here. If A starred is strictly greater in qualitative expectation than B starred, then for every C starred that is an extended indicator function, there is a positive integer n such that in A starred. Now, in A starred is just A starred added to itself n times. So what the copies are here is straightforward. In A starred is at least as great as in B starred plus C starred. So notice that if we think of the difference between A and B, we can think of n as being n copies of that. Then for any C starred, n times that difference will be at least as great as C starred. That's another way of formulating the Archimedean axiom. Now, the important point is those are just almost identical in basic structure to the 4 axioms for qualitative probability structures already discussed. And these 4 axioms are the basis for the following theorem. Let X, E starred, at least as great as an expectation, be a qualitative expectation structure. Then there exists a unique expectation function on E starred. Moreover, axioms 1 to 4 are necessary and sufficient so that there exists a representing probability measure on E. Notice that in the case of the representing probability measure on E, we don't say that the measure is unique. The measure is only unique if it has to also satisfy the requirements for the expectation function. And in general, that might not be the case. But as an expectation function, the expectation function is unique. So we have quite a contrast here to the qualitative probability structure in the sense that though the axioms are enormously similar, by this extension, 2 extended indicator functions, we're able to get a unique expectation function. And the axioms are not only sufficient to show there is a unique function, they are also necessary. Now, the proof of this is very straightforward. It just uses results already stated by Duncan Luce in the first lecture on extensive measurement, results that are given in Chapter 3 of Foundations of Measurement. Notice, just to quickly review, that necessary and sufficient axioms for closed extensive structures, that is, where the operation O is closed in the set X, are the following axioms. Weak order, weak associativity. Notice that we don't have to have identity here, though in the case of our extended indicator functions, of course, we have identity here. We have something slightly stronger because functional addition is certainly associative with strict identity. Monotonicity, which is just what we have in axiom 3, and goes both ways, of course, because functional addition is commutative, so both AOC equal to or greater than BOC and COA equal to or greater than COB as required here. The commutativity guarantees both ways. The Archimedean property, and finally, we want weak positivity. In the lecture, I think the concept of strong positivity, we can also use weak positivity for such extensive structures, AOB at least as great as A. Now, given those axioms, they're necessary and sufficient to prove there exists a phi, a non-negative real function phi, such that on X, or on the set X, such that A at least as great as B if and only if phi of A equal to or greater than phi of B. The additivity property we expect for extensive measurement. Phi of AOB is equal to phi of A plus phi of B. And third, the weak positivity property that for every element A in X, phi of A equal to or greater than 0. Well, we see immediately that we have such an expectation function because these axioms for extensive measurement directly correspond to the axioms for qualitative expectation structures. The changes are all completely minor. We certainly have a weak order. The weak associativity is in fact replaced by strong associativity with identity. The monotonicity corresponds to axiom 3 for qualitative expectation structures. The Archimedean axiom we have, the weak positivity will come from the second part of axiom 2. Let's go over here and remind ourselves of axiom 2. That the expectation of any indicator function for an event is at least as great as for the empty event, the indicator function for the empty event. And we get uniqueness of the expectation function as opposed to the standard ratio scale in the case of extensive structures, because we're requiring for the natural interpretation that the expectation of the indicator function of the whole space X is 1. That fixes, in other words, the unit. So we immediately get from the theorem that Duncan Luce stated in the first lecture on extensive measurement, the proof of the desired theorem 2 here about qualitative expectation structures. It's a familiar fact in the abstract study of structures and their application in various parts of science that sometimes relatively small changes in the structure will lead to considerable simplification. That's the case here. By going from events to the slightly larger structure of extended indicator functions, or to, we could say in another way of putting it, to non-negative integer valued random variables, we get a way of stating necessary and sufficient axioms that are almost exactly the axioms considered for qualitative probability structures, but with this requirement that they hold in the larger set, we're able to get the appropriate numerical representation. Examples of such extensions, familiar examples, are the extensions of the rational numbers to the real numbers to the complex numbers, satisfying different kinds of requirements. In one sense, the axioms we've just given then give a relatively satisfying answer to the provision of necessary and sufficient axioms to have the existence of a probability measure. The probability measure in general is not unique. The problem appears to be extremely complicated to give necessary and sufficient conditions directly on the events to have a unique measure. But I think it's fair to argue that for all probability work, we all really want to have an expectation function. We'll ordinarily work with random variables extensively, and once we are willing to consider the expectation of some simple class of random variables as we have, that's enough to make the measure unique. This concludes this lecture on probability representations, but I want to emphasize that many important topics that I've not had time to discuss are covered in Chapter 5. I mention especially the discussion of the qualitative analysis of conditional probability.